So we got two more chapters. Chapter 11 is a continuation of organic synthesis. Oh, by the way, I did a quick weight on our aspirin, and he gained weight.
Oh, is that supposed to happen?
Well, I looked it up, and apparently aspirin is hygroscopic. It'll pick up moisture from the air.
Oh.
So what I've done is I took it and I put it in a desiccator. Sit in there until we're finished here, and we'll see what happens. It's very unstable in humidity, so we may have lost some. Actually, gained water but lost aspirin.
That sucks if we did.
But at least we got that initial measurement, and
Yeah.
if we can't make sense of a second weighing, we'll take the first weighing.
I mean, I still have like the first laying in my paper, so I mean, I'll have both of them in there.
That's fine.
So
Nobody touched the board, so it's all up there still.
Oh.
Okay. All right. So in chapter 10, we introduced the general ideas surrounding organic synthesis in multiple steps. And we did talk a little bit about modifying the carbon skeleton, but most of the reactions we discussed were functional group transformations. And actually, if you're going to extend the carbon chain or the carbon skeleton of a molecule, you have to have functional groups, because apparently the alkyl groups aren't that reactive. At least not the well, you have to make them either electron rich or electron poor. And typically that means starting with something that's got a functional group on it. So we've looked so far at starting materials that only have a handful of carbons and are relatively simple in structure. But a lot of the more interesting compounds are much, much bigger, have more carbons in them. So we need to extend the carbon skeleton. And that means reactions that form and break sigma bonds. Now, if you just that makes sense, because if you break a pi bond or form a pi bond, you're not doing anything to the skeleton. It has to be a sigma bond that's eventually broken and or formed to modify the carbon skeleton. So in chapter 11, we're going to look at a method for logical proposition of a multi-step synthesis. And I think I mentioned that once before. It's called retrosynthesis. You actually work backwards from the product. And you look at the bonds that have to be broken, the bonds that have to be formed, and then you just reverse it. Once you're satisfied with your retrosynthesis, you just reverse it, fill in all the details like you would with any other synthesis. And the proper term is retrosynthesis analysis. Let's see. And we're also going to add some new reactions that help us modify the carbon skeleton. And those should be in that handout. Now, that's one of the reasons that once we get through chapter 11, and there are a lot of new reactions that are proposed in chapter 11, we get to chapter 21, we've actually skipped over, well, 9 chapters. Skipped over a bunch of chapters, and there are lots of other reactions that are discussed in those chapters. And then chapter 21 makes reference to those, and we haven't even looked at it. So the only reason I go to chapter 21 is because it talks about synthesis also. We have three synthetic chapters. But I want to get to 21 because it discusses synthetic traps. So when you do this retrosynthetic analysis, you may actually be walking into a trap. So we're going to try to figure out how to avoid some of those traps. Well, there's a pretty complicated molecule Taxol used in chemotherapy, cancer chemotherapy. And a lot of the synthetic procedures that organic chemists use begin with natural products. They isolate the natural product precursors, and then they just modify it. Sometimes it's a lot more efficient to do it that way. If we had to build this molecule from 2 and 3 carbon precursors, you're talking about a lot of steps. And you've probably already seen, I've seen you've done your homework. You've probably seen that with every step, your efficiency goes down. So sometimes it's more efficient to let the plant or the microbe build the precursor, and then you just modify it to suit you. Mm. All right, I think we've looked at these two already, where we react an alkyne with with another alkyl. Alkyl halogen, and we tack on a number of carbons on the end of that alkyne group, and then alkyl halide, excuse me, gotta get my terminology right. Then another possibility is to add a cyanide group on the alkyl group. Those are just two that we looked at in chapter 9. All right. Both of these reactions proceed by an SN2 reaction. Now, the one thing that you have to have for an SN2 reaction, well, two things actually. You need to have a strong nucleophile. So in that first reaction, your strong nucleophile is the hydride ion, right, the H minus. But since we're writing it in synthetic form, sodium hydride would be the compound that you add. But for mechanistic purposes, H minus would be the active group. And for the second one, you've got a strong cyanide anion that is the reactive group. And one of the differences is the first one is a 2-step process, and the second one is a 1-step process. So in the 2-step process, the hydride ion deprotonates the alkyne. That's why the alkynide anion is the reactive species, the electron rich or the nucleophile in this reaction, because of that first step. And then the second step is SN2 reaction, whereas our second example here is an SN2 reaction with 1 step. All right. Let's see. Well, I already described this. Right. The first step is proton transfer. You deprotonate the alkyne. And then the alkyne becomes the nucleophile on the alkyl halide. Now we're going to look at later, when we get to green chemistry in chapter, is it in this chapter? Yeah, I think it's at the end of chapter 11. We talk a little bit about green chemistry. Well, maybe not. Maybe it is in chapter 21. Anyway, just keep in the back of your mind, when we're developing these syntheses, we look at products that are discardable. In other words, they're not what we want. So we got to do something with them. So we either send them off as waste and they have to be treated, or we select a reaction that doesn't produce the waste. And that gives you a more efficient, actually a more cost-effective, usually, procedure. So in this case, the second one, you'd have these iodide ions floating around. They're not that toxic, but in large quantities in an industrial scale, they might be an issue. All right. That's just, we probably already looked at this, haven't we? I don't know if we have or not. We have these reactions in chapter 9. Yeah, it looks familiar. And then the second reaction, where it's simply the cyanide the cyanide ion is the nucleophile. And let's see. Oh, I missed the bromide on the end. Okay, that's the point of attack. It attacks the carbon, the terminal carbon on the bromide. And that would be a backside attack, obviously. And then you've added a carbon to the skeleton. If you only need one carbon, that's fine. Right? But if you need more carbons, then you probably want to go another route. Right? So you don't have to just add a carbon and then you have to brominate it and then add another carbon and then brominate it. Take you forever and your efficiency will go way down. Let's see. Did it give efficient? Yeah. Okay, so this first one we had 75% efficient because we had to go through 2 steps. Whereas the second one is 86% efficient. And that's a rough comparison because these are 2 different reactions, 2 different mechanisms. Okay. You look for structural features that surround the new carbon-carbon bond in the product to provide clues as to which reaction you're going to use. And that includes things like stereochemistry. Right? Do we have any bulky things sitting in the way? Also, or if it's a certain type of reaction, is it going to give us the wrong stereoisomer? And then what functional groups do you have to deal with? We're going to look at traps later, where if you have multiple functional groups on your precursors, then you could get the wrong reaction, because if you got a functional group here and one here, and they're both reactive to the nucleophile, then you could get a product that you don't want. So we talk about that, I think, in chapter 21. Okay, the reactants we call precursors. When you see a particular set of features surrounding the carbon-carbon bond in the target, you'll usually be able to draw the precursors for a reaction that would make that bond with practice. So, as an example, we already know that this reaction is going to give us that product. But if we look at it in terms of retrosynthetic analysis, we would focus in on the product alkyne. And that's what we did down there on the lower left. And then we'd say, okay, where's the bond? Since we're doing retro, which bond needs to be broken? And then when we flip it around, that's the bond that needs to be formed. So we got that squiggly line there that shows us that's the bond that's going to be formed on the carbon that's the amber carbon, the orange carbon. And then we're adding that R prime group, which is the other carbons that are going to be attached at that carbon. So if we look at, well, what would happen if that bond broke? What are we going to put in its place? Well, the first choice would be a hydrogen. Just tack a hydrogen there where you break the bond in the retro synthesis below. And then what's left over? Well, you have an R prime, but what are you going to attach to that? Most likely candidate is a halogen, because that excuse me, that makes the carbon on the R prime reactive. In other words, the halon draws electron density away from that R prime, which makes that carbon electron deficient. Okay.
So I was trying to mute my laptop.
Yeah. What?
I was trying to mute my laptop. It was going off there for a second.
Oh, okay. Are you watching the?
No, I just have it on.
Okay. All right. I forgot I had notes in here. I should just do the notes and then talk about the notes. So the new carbon-carbon bond in the product involves one carbon atom. They call it a red screen. That's part of the triple bond. And another carbon that's sp3 hybridized as part of an alkyl group. So if we go back and try to think about the molecular orbital modeling, the sp3 carbons are the ones that give us the reactive carbons. But the sp2s and well, they give us the carbocations. I should say it that way. They give us the carbocations. So to form a bond, one precursor would be a terminal alkyne and the other precursor would be an alkyl halide. So the basis of this method is that once you've got the retrosynthetic analysis done, you go through a transform where you just flip it around. And now the products of the synthetic analysis become the precursors for the actual synthesis. And you'll notice that when we do a retrosynthetic analysis, we have that double shafted arrow. That's just to distinguish it from a normal reaction mechanism arrow. And I mentioned the squiggly line already. That's the bond that is broken in the retro and is formed in the synthesis. All right. So I've already said that, so I'm not going to go into that. Well, okay. This is the other possibility. This is the other reaction where you have the cyanide. We want to form a carbon-carbon bond using the cyanide anion. So that means for the retro analysis, that's where we break the bond. And then what that gives us is, if we want a reactive carbon for the cyanide to attack, we know the cyanide is going to be a negative. It's going to be the nucleophile. So that means we need some way to make the carbon on the precursor a reactive site. And one of the easiest ways to do that is to attach a halogen to it, right? Like chlorine or bromine. And that will draw electron density, since it's electronegative, will draw electron density away from the carbon and then make it receptive to attack by the cyanide anion. Some of this makes sense. Some of it later doesn't. So frequently a target has more than one feature to consider when transforms are applied. Yep. In which case there could be more than one possible set of precursors. All right. What that means is if we want to form that compound at the top, right, we could break the bond near the on the alpha side of the alkyne, and then then our added carbon would only be a methyl group. Right? Or we could break the bond on the other side of the alkyne, and then our precursor would have to be some alkyne. In which case we would deprotonate the alkyne, and then it would attack the carbon at the halogen. I think that would be a better choice rather than trying to extend it on the right hand side, because the problem may be that the alkene end may be reactive. But in this case, if we break the bond, let's see, yeah, there's my cursor. If we break the bond, that's sitting off to this. Wow, that's almost off the screen. I wonder if there's a way I can. That's because it's chopping my letters off. Is there a way I can zoom this? There. I wasn't patient. Aspect ratio. Here we go. Yeah, now we can see everything. All right. Because when I put my slides together, they run right to the edge. I use all the space. All right, so we use the first method for forming a carbon bond, but we chose the point of breakage. We chose the precursors actually that would work the best. Let's see. So what if we're going to change a functional group? Let's see. This primary carbon came from the alkyl halide. Okay. Let's see. We want to end up with this ether on the right-hand side. So if we start with, we break that bond right there, how are we going to get to that one? Well, if we want that carbon to be a carbocation, or we want it to be electron deficient, when it'll be the electrophile, then a halogen would be a good choice. And then if we have a alkoxide, right, formed from this sodium alkoxide, then that would give us our nucleophile, and that should attack that carbon. So then if we write it, let's see, well, I thought we were going to go ahead and do it. So if we write it the other way around, then there's our alkyl halide, And there's our nucleophile. Now, I think by convention, I've seen it all different ways. Sometimes I've seen the precursor and the other reactant in normal position in a reaction, something plus something. But I think organic chemists like to put the nucleophile on the arrow, because if it's going to be a multi-step, you're going to have a one for that one, then you're going to have another one, and then you're going to have another one. So I think that's why they put them on the arrow rather than make them a reactant. Okay. So we're going to examine the target for a feature that could be made from a known reaction. Then we apply a transform that undoes the reaction you have in mind. Once you write the retrosynthetic and analytical steps, then you just flip it around. And then you write it in a form that would look like a recipe. All right. Oh, this is a little history. Retrosynthetic analysis was developed in the first part of the 20th century by Elias Corey, Harvard University. Oh, yeah, he got a Nobel Prize for it. Took him a while, 1990. Usually the Nobel Prizes come way, way later. They have to decide whether the work that you did is accepted by the scientific community, has produced results in the scientific community, and that takes a lot of time. So if you're going for a Nobel Prize in your early 20s, you're going to have a long wait.
Like how long? Like 20 years?
Yeah, it varies. Yeah. I don't think Einstein had to wait that long. His first Nobel Prize was for the photoelectric effect, and it was pretty well. I mean, it caught on like wildfire. So it was maybe 7 or 8 years. It didn't take long. Okay, so this guy was working at Elias Corey was working out of Harvard University. That was before Harvard University made itself irrelevant through embracing woke ideologies and cancel culture rather than academic excellence. That's my editorial comment. So, if we're given the product that we want, this 1-methoxypent-2-ine, notice we have an alkyne and we also have an ether in there. And the restrictions are that we have 3 or fewer carbon atoms in our precursors. So how many carbons do we have? 1, 2, 3, 4, 5. We have 5 carbons in the skeleton, then we have an ether group and then another methyl group on the end. All right, so we could 1, 2, 3 or fewer. All right. This is going to take several steps. So what reactions do we know that will produce the results? All right. So I usually start from the outside and work your way in. Look for places where you can make those connections. All right. Because the target contains a continuous chain of 5 carbon atoms, compounds we may use as our starting materials can only contain 3 carbons each, and the synthesis of this compound must contain at least one reaction that forms a carbon-carbon bond. Right? So if we have 1, 2, 3, 1, 2. We could alkylate on the left, we could alkylate that alkyne with an ethyl group. And then on the other side, we could alkylate the alkyne from the other side. So that's where that squiggly line comes in. Our first approach is to break that bond, right, where you have carbon 4 and 5. And that means we need a brominated ethane. And then we have our alkyne. Okay, now what step is going to take? That step of those two precursors, only bromoethane is acceptable for our starting material because it contains 3 or fewer carbons. All right, okay, I'll go with that. The 3-methoxyprop-1-ine, which is the other precursor, contains 4 carbons. All right, so it's going to have to be synthesized also. So we take that one next, and we say, how do we make that? Well, if we brominate 1, 2, 3, 3 carbons, okay. If we have a brominated alkyne, and then we use an methoxy to attack it, then that will form the ether with a Williamson ether synthesis. Okay. So now we flip things around, right? So we take the brominated alkyne and we treat it with sodium methoxy, and then we get this precursor, and now we treat it with the ethyl bromide in a 2-step process, and that gives us our product. There are alternative ways. Right, here's one. Let's see, will this work though? Instead, we're going to break that bond, and that gives us bromomethoxy methane as one of the precursors. And then if we have these 2 compounds come together, how do we get this 1, 2, 3? That's got 4 carbons, so we got to break a bond here. And that's another way to form precursors. And that's another possibility. So there's more than one way to get to the end products. Okay, what if we want to go from this alcohol to this cyanide? It looks to me like we're going to replace that hydroxyl with a cyanide. Right? It's going to be a nucleophilic substitution of some kind. Right? So will a carbon-carbon bond form necessary? Yes. So that the hydroxyl bond must become a cyanide bond. Right? SN2 reaction, can we do an SN2 reaction that will reverse that bond breakage? Well, if we start with a brominated and we hit it with cyanide ion, let's see. Yeah, we need 2 steps. Right? We can't just go in and remove the hydroxyl. Hydroxyl is not a good leaving group, but bromine is. So that's why we have to brominate it first with a phosphorus tribromide. And then we can go in with an SN2 attack and remove the bromine and form the carbon-carbon bond. Okay. We talked about epoxides last time, didn't we?
Yeah,
Yeah, I think so.
I vaguely remember.
Yeah. Oxyrain.
Yeah,
Yeah, oxyrain. Ethylene oxide is a more commonly used name. So we're going to form a new carbon bond, right, using that methanol. And let's see. Actually, we're not going to form a carbon bond. We're going to form an ether, a 2-methoxyethanol. Methanol is the solvent, and the alkoxy anion is the one that forms the bond with when the ring opens. But if we want to form a carbon-carbon bond, we have to change the reactants, right? We can form a carbon-carbon bond with cyanide. So when that ring, these oxyrains are very, very reactive because of bond strain primarily. I think we mentioned that in chapter 10. So if we let's see, all right, we're switching gears here. Sorry, caught me off guard. If we want to open that epoxide, we're going to form we want to form a carbon-carbon bond on that alkyne. And in order to do that, we can use the epoxide. It has 2 carbons in it. And notice that in the product, we have 2 carbons with a hydroxyl on the end. The hydroxyl comes from that oxygen in the epoxide. And then there's a bond that forms. All right, in order to do that, we have to, right, the carbon that's attached in either one of those carbons in the epoxide is electron deficient because they're both attached to an oxygen, right, which is electronegative. So it makes them electrophilic. And all we have to do is make that alkyne nucleophilic. So we hit it with hydride, right? It extracts that hydrogen. It leaves the electrons behind. Notice the curved arrow. And that gives you a formal negative charge on the end of that alkyne. Now that is the nucleophilic attacker. And in the second step, an SN2 reaction is very strong nucleophile. So it will promote an SN2 reaction. It'll attack that carbon, form the bond, and then those electrons are from the bond that's broken, transferred to the oxygen. But that gives you another alkoxide. And in order to stabilize it, right, we do a proton transfer workup with an acid. Right, just transfer a proton to that alkoxide. And now you have a stable alcohol.
so does that oxyrain basically just unfold?
Yes.
Okay.
Yeah. Yeah. It's just goes like this. You got oxygen, and we break this bond, and those electrons go here, and the attacking species. Let's see. In this case, it was an alkyne. That they go that way. These electrons, let's see, we put the electrons. These electrons attack that carbon. That forms the bond. And then this opens up and gives you the there, that negative charge. And then down here, you've already formed a bond between that.
And,
Yeah.
my mind's blanking.
Huh?
I was trying to tell you what it was. My mind just like totally slipped from me.
But it'll stay like that unless we have a third step where we hit it with acid. Right, the sodium hydride, let's see. Right, is like this. And you got this, this is a spectator. And this, like that, that's what removes the hydrogen from this alkyne. But you still got that sodium in there. So you're actually working under basic conditions. So there are no protons available to complete to make that whole. Okay, so you have to do an acid workup afterwards. All right. There's another way to approach this. Is use organometallic compounds. Organometallic compounds well, actually, no, this is not an organo because there's no carbon in there. But organometallics, one possibility is alkyl lithium compound. And you can get, if you don't want a triple bond on there, right, and you don't want to have to deal with the triple bond afterwards, you can use the this ethyl lithium compound. And what it actually does, see, the lithium is a strongly positive charge. So what it gives you is there. It gives you an anion that is now your nucleophile. And that will attack the carbon also, just like we showed in the previous one. And when it opens up, then you still have to do an acid workup. You still got the, okay, here we go. Alkyl lithium is one. Grignard reagents are the other. I missed that one. So Grignard reagents will also give you the alkyl anion. I think Grignard, I don't know if he got a Nobel Prize for that one or not. It might have been too early. So they behave as nucleophiles. And we're going to show this on the next slide. Many of these reagents are available, but sometimes you have to make them yourself, especially if they're particularly unstable. So this is a generic alkyl lithium reagent. And we had a haloalkane and then lithium metal. That's it. I mean, it must be finely divided, right? Very finely divided. Lithium metal that's used to attach to the alkyl group. And then that's your reagent. You can use that reagent. Or the Grignard reagent, you start off with a haloalkane, and then you hit it with magnesium metal. And that gives you the Grignard reagent with the magnesium. It's usually written as some alkyl group and then magnesium here, and then the halogen on that side. Now this is extremely electronegative, And this magnesium, I think there's some, I always forget that word. Shoot. Some movement of electrons this way, and magnesium enhances that. Now there's a more detailed explanation coming up. I probably should just let it happen. Fluorides are usually not used, I think, because they're too small. They're not very stable. So the X in either one of those, well, the X in the Grignard reagent would be more reactive with an iodide than with a bromide or a chloride.
Is it larger?
Yeah. Okay, here he is, Victor Grignard. He discovered this and got a Nobel Prize for his work in 1912. Okay, I thought he worked at the end of the 19th century, like in the 1880s or 90s.
Can you die and still get a Nobel Prize, like your work after you die?
Posthumously. Yeah. Lots of times, I've seen Nobel Prize given for several scientists that worked on the same project, either together or separately. And if one of them dies in the interim, then they'll still include his name on the prize, and they'll split the prize between the living one and the estate.
Yeah. What do they get, like a bunch of money?
Yeah,
Okay.
lots of money. I forget the scientist's name at in Colorado, who took his Nobel Prize, and part of the money he used to start the FET simulations. Have you seen those?
Mhm.
They're computer simulations that you can go to online, and I use them in physical science class, particularly because it's all online. And you can simulate various things, like you can simulate sky's the limit, actually. Various chemical reactions. You can simulate the effect of pressure on a boiling liquid. They're pretty neat. And he used it as seed money to get it started. And now it's self-sustaining. Yeah, I'm glad he did it.
This is cool.
Yeah. Okay. The Grignard and the alkylithium reagents are the ones that are they're the go-to reagents for this type of reaction. But you have to use the right solvent. That's critically important. For the alkylithium compounds, you need pentane or hexane are often used. You don't want to use a protic. You want to use an aprotic solvent. Diethyl ether can also be used, but it's probably more hazardous. You have to prepare these alkylithium reagents immediately before you use them. So that's part of your reaction workup. For the Grignard reagent, usually ethyl ether, diethyl ether, sometimes they call it that, or tetrahydrofuran are used for Grignard reagent. So they're aprotic also. And these molecules are used as solvents because of the way they activate the Grignard reagent. The lone pair of electrons from the ether molecules form a complex with a magnesium. And we'll show it in your next slide. This complex helps stabilize the organometallic and increases its ability to react. So that's what it looks like. We get these ethers. They form, I wouldn't say bonds, but they associate with the magnesium and stabilize it. So the functional carbon atom has been reduced. In other words, it's made into an anion. If we just had the, okay, let me illustrate it this way. If we just had the R group, and I'm going to add a carbon out here, attached to a halide, this would be the slightly negative and this would be the slightly positive. So this would be the electrophile. In other words, a nucleophile would attack that carbon. But if we do this, then the we actually create, let's see, do I have it illustrated? No, we actually flip the electron densities here so that now this becomes like that. So now we get a nucleophile instead of an electrophile out of that carbon. I left out the carbon, it should put a carbon. That's what the Grignard reagent does.
So on the slide, it just has Mg with the X. So do we need to put the dash in between the magnesium and the X, or does
You
it
don't have
matter?
to. You don't have to. You're right. That's fine.
Can you do that with the carbon over there? Or is it just
Yeah,
certain atoms?
you can do it that way.
I didn't know if it was just certain ones or
No, if you want, if you're going to say something about the bond that you're illustrating, then you want to put the dash in there so you can do things with it.
Oh,
But if you're not going to do anything with it, you can just write it like that. So here's what it would look like. This alkyl halide, then, if we treat it with metal, we can treat it with lithium, magnesium. Actually, you can treat it with several different metals, depending on your specialty. And what we see on the left-hand side, the alkyl halide gives us a carbocation. But on the right-hand side, these organometallic compounds gives us a carboanion. So that becomes the nucleophile. And these are some common organometallics. I think they're in your book. Methyl lithium, butyl lithium, tertiary butyl lithium, phenyl lithium, methyl magnesium bromide. That's your Grignards. The lithium organometallics in the top, and they don't have a special name. The Grignards are on the bottom. You can even form Grignards with aromatic compounds, the phenyl magnesium bromide. If you want to add an aromatic group onto your skeleton, then you can use a Grignard to do it. Okay, what are the limitations? These are powerful bases, which means if there are any protons around, that's why we use aprotic solvents. If there are any protons around, they're going to grab them. So, if we're trying to attach this methyl group to that alpha carbon here, we're not going to get it, because that Grignard reagent will go in and deprotonate this hydroxyl. That's all it'll do. It won't give you what you want. Right? So that's why we use the well, okay, there are two things going on here. We use aprotic solvents, plus we can't use the Grignard reagent on acidic compounds with acidic hydrogens. So what we're going to look at in chapter 21 is how do you, if you want to use a Grignard reagent, how do you protect yourself from that reaction, that undesirable reaction? One way is to go through a previous reaction that attaches a protecting group. on that oxygen in this case. Right. Then you complete the reaction and then you remove the protecting group and reconstitute the acid group. All right. Okay, partial list of functional groups we cannot use are alcohols, amides, primary amines, secondary amines, carboxylic acids, terminal alkynes, because they all have acidic protons on them. So those are off limits for direct reaction without the other without using a protecting group. But I mean, it's still a problem if you have to go through 2 extra reactions to get to where you're going, then your efficiency is going to go down. So there are trade-offs.
So with that, like with money saving cost wise, sometimes like in my head it's cheaper to just do like one reaction, but what happens if whatever you use is a lot more expensive? Does that make sense?
Yeah,
Like, is that a thing? Like, is it cheaper to do one reaction, or is sometimes the one reaction just very expensive?
Yeah, they're
They come both.
right. When we don't talk about that here, but when you're designing a reaction sequence for an end product, if your precursors are so expensive that you or the company can't afford it, then you may have to tolerate inefficiencies and just make lots of it. Yeah. That's like my favorite reaction is the Haber-Bosch. We have nitrogen and hydrogen make ammonia. The efficiencies there are in the neighborhood of 15%. But if you get your reactor running, your process running, and you run it 24/7, then the output that you have economy of scale. When you produce a lot and you don't have to shut down for any reason, then you can the economics are workable, even though efficiency is low. So, can we open an epoxide ring with a Grignard? Yeah, you bet you can. Right, there are no acidic hydrogens on that one. So it's going to go in, and that phenol, the mechanism's down there. That phenol anion attacks the same carbon that we saw before, opens the ring, and then we do an acid workup, and we get our let's see, 1, 2. That is a phenol.
I'm confused as to why it's not a benzyl.
Well,
Phenol just has the one bond. In my head, it works like that, and then the
Yeah.
benzyl has the 2 bonds. Unless
well,
I don't know.
yeah, a valid concern. Let's see how that works. This would be a phenol group attached to something. This would be a benzyl group attached to something. So if it's attached to another carbon and then a hydroxyl, then the benzyl would be this part. But if you went phenol, then you could say this is the side group. You could say that. Actually, we don't have to put the one in there because Well, we do. It's attached to the number one position. Oh, wait a minute. That's the one position. Two. No, the all is one. The all is on the one. Yeah. So the phenyl is attached. Let's see. To phenyl ethane 1-all. No. There we go. That's what I would name it. Okay.
They just don't have the one in there.
Oh,
They have it all written out together.
2-phenylethanol?
Yeah.
2-phenyl. Oh, I wasn't even looking at that.
Yeah.
But you were sitting there checking me out.
Yeah.
Yeah, right. I guess if you don't put the one in there, then it's automatically on the one carbon. All right. So these are different ways that we can use that we can form carbon-carbon bonds with the epoxides. And we've talked about these already. This is just a list of them. All right, 4 or fewer carbons to make this compound. 1, 2, 3, 4, 5, 6, 7. We've got 7 carbons. So we could use a 4-carbon compound and a 3-carbon compound to construct this molecule. So does the target have bond arrangements? How many of these bond arrangements are there? Well, let's see. If we go this route, 1, 2, 3, then that means 1, 2, 3, 4 over here. If we go this route, 1, 2, 3, then we got, it looks like we got 2 bonds to make.
So on that right hand one, why won't we count the rest of those bonds? And then that's why we just stopped.
Say that again.
So like on the right hand one where it's highlighted yellow, why
Yeah.
doesn't it keep going? Why does it just stop?
Yeah, that's a good question.
I don't understand why we wouldn't count those in.
Yeah, I mean it 1, 2, 3, 4. Oh, that's 5 carbons.
Oh, 4 fewer.
Yeah. So for the first bonding arrangement, we can apply the following transformation. All right. And we can put an epoxide on the end, and that gives us a methyl anion. For the second bonding arrangement, we can apply the following transform. Okay, so the author is proposing actually 2 reactions to get where we're going. No, he's saying one or the other. If we're using an epoxide ring opening, that the reason we're using an epoxide ring opening is to give us that hydroxyl. That's the simplest way to get the hydroxyl if we start with an epoxide. So if we have a starting material of 1, 2, 3 carbons on that Grignard, and we have 1, 2, 3, 4. That's 3 and 4. How many carbons did we have? 1, 2, 3, 4, 5, 6. Oh, that would work. That would give us 7 carbons. Yeah, that one would work. We use the Grignard with a propyl Grignard, and then a 1, 2, 3. I don't even know how to name that. That epoxide. So that would
So
work.
basically all we would do was just close it and make it turn into like the oxy or the epoxide.
Oh,
Is
how
that
would
what it's on?
how would you form the epoxide? How would you
Yeah.
make it? We haven't got to that yet, have we? No, that's on a slide coming up. Right, we're talking about these epoxides as if they're magical, right? Well, they're off the shelf, but we have to make them.
Now, I'm assuming these have a lot of like strain. The epoxides.
Yeah,
Okay.
lots of strain. That's why they open so easily. But we have to be able to form them, right? And that's coming, I think. Let me see. What? Or did we get that in chapter 10? How to make epoxides. Let me look. Let me look. I think we did. Chapter 10. Here we go.
I remember like one few slots on it.
Ooh, how'd that get upside down? Is yours upside down?
Yeah.
Okay, there's an epoxide. You got to read upside down. Yeah, here it is. Formation of an epoxide. So we have a halohydrin. Right? On one carbon, you have a chlorine in this example, and the other one you have a hydroxyl. And then you're in basic conditions in diethyl ether, sodium hydroxide and diethyl ether. And that gives you your terminal epoxide. Okay. So we have talked about that already. All right. Alkylation of alpha carbons. All right. When the subsequent discussions that are coming talk about adding carbons on the alpha carbon of a carbonyl. So we've got these two examples, two carbonyls. One is has an aromatic, and the other one is a cyclocarbonyl. What we find is that we cannot we can't form the carbon-carbon bond here. There's no reaction. All right. So what do we have to do to correct that? Let's see. We're discussing here. No reaction occurs when an aldehyde or a ketone, right? So ketone is the second one, the aldehyde is the first one, is treated with an alkyl halide alone. When a strong base like sodium hydride or sodium amide is added first, alkylation can take place at the alpha carbon, at the carbon atom adjacent to the carbon oxygen double bond group. So we're saying that for something like this, this is an alpha carbon and this is an alpha carbon. Okay. One adjacent to the carbonyl.
So it's going to be symmetrical.
Yeah, this is going to be symmetrical. All right, so we could get bond formation on either side, and it doesn't matter. Because all you have to do is flip it around, and they look exactly the same.
Yeah.
So we have to activate. We have to activate the precursor with a strong base. It's going to deprotonate. So for the first one, the alpha carbon has a let's see, we end up with a new carbon-carbon bond at the alpha carbon. And for the second one, likewise, we get a carbon-carbon bond using an alkyl halide. Right, the methyl iodide in the first one, and the 1, 2, 3, 4, 5, 6 no, 6 hexyl bromide. The hexyl bromide in the second one. All right, what's the mechanism here? Okay, there's the and it doesn't matter if this is a ketone or an aldehyde. So in this example, that looks like a ketone, right, because there are no hydrogens shown on the left-hand side. So what happens is the base goes in and deprotonates that alpha carbon and forms the anion. And so now this is the nucleophile that will attack the alkyl halide. And not only that, it's stabilized by resonance. Right, so in this case, we've got, let's see. Yep. And then we got this one and that one. Okay, this is resonating with, and we didn't do a lot of this. How do you form a resonant? How do you do an enolate? Well, these extra electrons transferred over here. That makes this, that takes the negative charge away from that one. But then this forms a double bond, and those have to go up here like that. So that double goes away, and now this one is negative. So this resonance stabilizes the molecule, but still it resonates, but it's not equally resonant. In other words, the enol, which is on the right-hand side, is the minor component. There's just enough of it to stabilize the what am I going to call that? Ketoanion? How about that? So the reaction still takes place with the alpha carbon off the ketone. And so now it attacks the alkyl group, and the bromide is the leaving group, and we form that bond. But we have to have the base in there. It has to deprotonate. It has to be a very strong base to deprotonate that alpha carbon. Now, in our examples, there's only one alpha carbon on that first choice, right? So it has to attack there. The other one, you have two alpha carbons. They're indistinguishable from one another. Let's see. All right, now we're gonna switch gears. Right, we got a different precursor, 2-methyl cyclohexanone. All right, so now we have unequal, non-equivalent alpha carbons. Which one? This leads to regioselectivity. In other words, we're going to form a bond either at the alpha carbon, the more substituted alpha carbon, or the least substituted alpha carbon. Right, the two possibilities. Right, so once that happens, you're going to have a carbon bond on the least substituted side, or a carbon bond on the more substituted side. Those are our choices for this ketone. All right, how do we choose? What conditions tell us that we're going to form the bond. In this case, we can be selective with the use of the base, right? Which alpha carbon is going to be deprotonated? Yeah, deprotonated. Well, the LDA, or the lithium diisopropylamide, at low temperatures causes alkylation to occur at the less substituted alpha carbon. That's probably, let's see, I don't want to misspeak. That's probably due to steric hindrance. You don't have that methyl group in the way. And LDA is a big molecule. Alkoxide bases. Well, now it's going to make me a liar. Alkoxide bases tend to substitute on the alpha carbon of the more substituted ketone. Right, so there must be another explanation. Let's see what it is. All right, for LDA, we're deprotonating. Right, so when we deprotonate, we get stabilization, right, like the enolate resonance, and then the alkyl bromide forms a bond with that alpha carbon. All right, that's what it looks like in the mechanism. Right. What if we use an alkoxide? An alkoxide tends to attack. We still get enolate stabilization. All right. All right. Now, why? That's the question. Why does that happen? Oh, I see where we're headed. Okay. When the LDA deprotonates the less substituted carbon, the products are heavily favored. In other words, we look at the energy diagram and you see that the products are much, much lower in energy. This is essentially irreversible. Right? It doesn't go back the other direction. Whereas if we deprotonate the more substituted one, that is the products are not heavily favored. You're in an equilibrium situation. So the difference between the two is we're looking at, for A, with the LDA, we're looking at kinetics. How fast does it happen? And for B, we're saying, what's the equilibrium situation? In other words, it's reversible. Okay. And here's the talkie points. All right, so I was on the wrong track. They're both about as bulky as, one is about as bulky as the other one. And they're both bulky. But the result is mainly from being a much, it results mainly from LDA being a much stronger base than tertiary butoxide anion. LDA is a much stronger base. All right. There must be more to the story. The product side, being a stronger base, the product side is favored. Whereas the tertiary butyl anion, the products are not favored. All right. So for a reversible reaction, okay. Reversible reactions are under thermodynamic control. We've covered thermodynamics.
We talked about thermodynamics last week. We were talking
Oh,
about the copper. Like, we
yeah.
just talked about it.
No, it's coming up next chapter, chapter 16. Thermodynamic control. In other words, thermodynamics predicts whether you the likelihood of a reaction going to completion. But it can go both directions. And kinetics is what happens in between with the energy barrier. So if there's not much of an energy barrier, then you're just as likely to go forward as backwards. So reversible reactions are under thermodynamic control, and the products are in equilibrium. For competing reactions, they can interconvert. So I think what they're saying is product one, product two. Actually, that diagram doesn't make a whole lot of sense. I thought there was only one product. All right, if we go back here, right, that product versus, well, that's the same product. Now, if we're saying that the reactants become products and the products become reactants, then that makes sense. But there's equilibrium between the reactants and products, in my way of thinking, and they can interconvert. Right. So as with any equilibrium, the species that's the most stable ends up being present in the greatest abundance, regardless of how fast it is produced. So this is thermodynamic control when you have an equilibrium and you have a very small barrier, energy barrier for going forwards or backwards. That will give you thermodynamic control. Kinetic control operates for irreversible reactions where the barrier is so large, the energy gain from the forward reaction precludes a reversible reaction. And these are under kinetic control. How fast does the reaction go? All right. So this is said to be under kinetic control. So reversible reactions are thermodynamic control. Kinetic reactions are irreversible. That just summarizes it. So what we're saying is that LDA is under kinetic control and tertiary butyl oxide anion is under thermodynamic control. Now, how does regioselectivity fit into that? Okay, so if we have the LDA forming the enolate anion, where the anion is on the less substituted carbon, we find that the less substituted carbon that when we're trying to resonate with the enolate that has the double bond on the less substituted carbon, it's less stable. And the more substituted one is more stable. The trialkyl substituted carbon is more stable. Right? Those are the main differences between these two reactions. All right, how does that feed into our discussion? There's one more piece to the puzzle. How the base dictates regioselectivity. In the deprotonation step to produce the enolate anion, which enolate is formed faster and which one is more stable? All right, the kinetic control, the enolate would form faster. right? Kinetic is fast, and more stable is the thermodynamic control. So deprotonation of a ketone at the less substituted carbon is faster, leading to the kinetic enolate anion. It occurs with fewer attached alkyl groups because there is less steric hindrance. All right, so steric hindrance does play a part. Deprotonation of the ketone at the more substituted alpha carbon is more stable. And that all right. The energy barrier is very low for the thermodynamic formation of the enolate. If the energy barrier is low, I don't get the connection. I guess it's a case of memorization. Sorry.
It's okay. I probably wouldn't have picked up on it anyways.
So let's see, if we're going to use alpha alkylations in a synthesis, this is going to allow us to form a carbon-carbon bond. Yeah, we're going to form carbon-carbon bonds. And we can select which alpha position is, if they're unequal alpha carbons, then we can select which one based upon the base. Right? The stronger base, and just because LDA is used doesn't mean it's the only possibility. If it's an extremely strong base, then it's going to attach on the less substituted carbon. And the weaker base is going to form the carbon bond on the more substituted carbon. All right. Synthetic traps. All right. They come in several flavors. I stuck this, that's why it doesn't have all the decorations. I stuck this one in here because it's easy, once we get into the subsequent slides, it's easy to get lost. So synthetic traps reference regioselectivity. That's one possibility. And we can subgroup here stereoselective. Or you can separate it out as a separate item. Regioselectivity means which carbon are we attaching to. Stereoselectivity means are we usually backside or front side, or doesn't matter. Multiple functional groups, or chemoselective. That's where you have more than one functional group that's active, and you think you're going to get a reaction at one site, but either you don't get that one and you get the other one that's more reactive, or you get both of them, and it just creates a mess. An example that we're going to discuss is the proton transfer versus nucleophilic substitution. As an example. SN1 or SN2. One or the other. And do I have a third one? Yeah. Loss of functional groups in the intermediate step. So your reaction, what we're saying here is if you put a reaction step into your sequence and it ends up removing a functional group that you need for the next step, then the chain's broken. You can't go any further. That's another trap. Okay. So if we're going to try to form this compound on the left with a terminal hydroxyl using a terminal epoxide and a Grignard reagent, right? Now we've proposed this retrosynthetic pathway. Now we're going to flip it around and say, will it work? So the less sterically hindered carbon is attacked under basic conditions. And so we set up these conditions with a Grignard, and what we get is, let's see, is that the same compound? No, it's not. It's a different compound, right? So we have a secondary hydroxyl rather than the primary hydroxyl that we actually get, right? So that's one possibility. We get the wrong product because it's regioselective. It went to the wrong carbon. Right. Is that obvious? We have this, this, and then that. Okay. So when the Grignard attacks with its 1, 2, 3, with its propyl group, and this is negative. So this is going to attack that carbon, and then this is going to open that one up. And what we end up with is let's see. 1, 2, 3. So it's supposed to be on the end. I messed up somehow. Oh, this opens up here. So actually, I've turned it upside down. Right, so this is 1, 2. So this is 1, 2. So there's the hydroxyl that shows up here. We do the acid workup, of course. And let's see, it's got 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 5, 6, 7. And it ends up on the second carbon rather than on the first one. Oh no. Yeah, right. What we wanted was a methyl group on number 2 carbon and the hydroxyl on the end. The other possibility is if we use a strong base, if we attack this okay. Oh, I do have commentary. We tend to focus on just the specific change that we want, and we sort of are blinded to the other possible changes. All right. Yeah. Where's my cursor? Get that out of the way. So when we apply a transform that undoes the epoxide ring opening, in which case the precursors of the right reaction would be required. All right. So it's not working the way we want it to. Problem we run into is when we put the reaction in the forward direction, the Grignard reagent is also a strong base. So when it reacts with the epoxide ring, it attacks the less highly alpha substituted carbon. So the wrong product is synthesized. Okay, so that's up to 1144. I want to see where are we going with 1145. To produce the desired target, the nucleophile would have to attack the more highly alkyl substituted carbon of the epoxide. It would have to attack the other side over here in order to get the product we want. Acidic conditions can make the difference. So if we come on, get out of my way. There we go. In which case the epoxide oxygen is protonated, carries a +1 formal charge. All right, so if we introduce an acid, it protonates. Yeah, if we use a strong acid, it will protonate that oxygen. Right. Then the strong base will extract the hydrogen. And I don't see what good that does us. This strategy won't work for our synthesis. Yeah, it won't work for this synthesis. I think there was a reaction we had in the past where we had basic conditions versus acidic conditions, and protonating the oxygen helped the reaction to proceed the way we want it to. But in this case, it won't, not with a Grignard reagent. This regiochemistry prevents making the desired product. All right. That's just an example. We tried to fix, but it didn't work. Okay, so that's the sequence here. We said, okay, I want to do it this way. When I try to do it this way, I get the wrong product. Right. So I said, okay, my fix is basic conditions. Let's make acidic conditions. Right. Well, acidic conditions, and then when you add the Grignard reagent, it just goes and deprotonates it. And it doesn't do what we want it to. Okay. Another trap. Chemoselectivity. In other words, two or more functional groups. So if we want to make this product and we say, okay, we want to use a propine and a 3-bromo-propane 1-ol. Right? So we flip it around and we deprotonate the alkyne, right? And we think, well, if I deprotonate that alkyne and make an anion out of it, it's going to be a strong nucleophile and it's going to attack the carbon attached to the bromide. Guess what? It doesn't. It goes and deprotonates. Right? So it produces the desired reaction doesn't take place. In other words, we want to extend the skeleton at the bromide end, but instead it just deprotonates that oxygen, that alcohol. Proton transfer, and then that's it. Can't do anything with it. All right, so that's just another trap. We wanted nucleophilic substitution here, and we got proton transfer instead. Okay. All right, I'm not going to spend a lot of time on this because it just takes a lot of practice. It takes a whole lot more practice than I've ever had. So I'm not going to hit you too hard on that one. The authors talk about proposing, just making up stuff. Right? I want to make this compound. How do I do it? Well, that's okay as long as you know enough to pick a product that you have the skill sets for making, right? And at this stage, that's unlikely. And then swapping with your study group partners, right? Create something and say, all right, have at it, and you swap, right? All right. So how would we make this alkene from that precursor? Okay. Does a carbon-carbon bond form? Yep. So a carbon-carbon bond does form. We need to use that reaction. What functional group could be converted into an alkene? Well, alcohols can be converted into alkenes. Right? We just undo a dehydration. Or we could undo an epoxide ring opening. Right, so which one would work? The starting material is a halohydrin, which can be a precursor to an epoxide. Right? So we can make the epoxide from the precursor. Right? We saw that in the previous chapter. So once you've made the let's see, make the epoxide, then you make the secondary alcohol, and then you use heat and phosphoric acid, and that will give you the alkene. Now let's see. Remember how that works? Yeah. So once we get to this point, then we go in with our phosphoric acid. Phosphoric acid. And yeah, and that attacks that, forms bond there, and that gives us water as our leaving group. Makes a good leaving group. So then what happens is these electrons go here. Right. These electrons go here, and this leaves as water. And that forms a double bond. I'm surprised I remembered that. Okay. Oh, green chemistry. All right. So everybody's talking about green this and green that, but in many cases, it's a good idea. One of the ways that you reduce impact on the environment and safety problems is you reduce the scale of your reactions, and that's what we did in the lab. When I was going through this mess, we would have reaction vessels like that and condensers that were this big around, and we'd catch huge amounts of product. But we did the small vessel and distilled over in small amounts. Right? That's one way to reduce the impact on the environment and safety concerns. What you want to do is essentially avoid the accumulation of hazardous materials, or not just avoid the accumulation, but using hazardous materials. You want to use the least hazardous materials available to you within cost constraints. So that might require different reactions, different techniques, or even different technologies. And reference a website here for green chemistry. This would probably cover all chemistries, not just organic. So here's two reactions, end up with the same product. One, we use bromine and acetic acid. and that brominates the alpha carbon. Less hazardous would be used to use hydrobromic acid in hydrogen peroxide and water. You get the same reactant, same product. But it's less hazardous. Bromine is hazardous. Now, at room temperature, bromine is a liquid. So I wouldn't think that volatility would be a problem, but perhaps they're not showing us that you have to heat it to make it work, which would volatilize the bromine. And it doesn't say how concentrated the hydrobromic acid is either. Use different solvents. So DMF is readily absorbed through the skin and is a liver toxin. That's dimethyl formamide. To give you that product. So what if we use a solvent like water or ethanol, which favors an SN1 and E1 reaction? Aprotic solvents favor, well, if the stereochemistry, let's see, that would work, right? We would have a backside attack on that carbon attached to the bromine and would give us the azide on the backside, right? Rather than going through. Can we do that though with an SN1, right? We have, I don't know, we're going to produce a mixture. If an SN2 reaction is required, such as the one in 1155, you might at first consider using an aprotic solvent. In this case, SN2 reaction would take place in either water or DMF because the azide anion is a strong nucleophile. Okay, so water could be a solvent. Let's see. Yeah, okay, water would work. Right? It doesn't matter if it's protic or aprotic. Water would be a greener choice in that case. Say for synthetic routes, all right? Yeah. That compound, excuse me, diazomethane is explosive. It's extremely reactive. That wouldn't be a particularly good choice. We used sulfuric acid and methanol. You should get the same product and be safer. Okay, how about minimizing byproducts? If we do this reaction, where we're forming, this goes through a sequence of steps using that ethoxy. No, tertiary butyl. Tertiary butyl anion would form the triple bond, but it would also leave us with unusable byproducts. So we got to get rid of those. What if instead of using the bromide compound, we use an epoxide? I just open the ring, and that would give us no byproducts. And then we could go from that step. Well, that doesn't help me. Can we form a triple bond with that hydroxy halide? Go figure. Because you're not getting the same products with that one step. But you don't have any byproducts either. I think that's why I stuck that note in there. There's not alternative synthesis, but an illustration of waste economy. And then there's a calculation that we often do. Well, I guess organic chemists do it. Is percent atom economy. So you take the mass of the atoms in the desired product and the mass of the atoms in all the reagents, and that gives you a percent value. Okay, that makes sense. I mean, that goes back to Lavoisier, right? Conservation of mass, right? In the second example, that would be 100%, wouldn't it? The mass of the atoms in the desired product is the same as the mass in the reactants. So that would be 100%. Whereas if we calculated it for these, for the first reaction, we would end up with 20.8%. Well, that's not very economical. Percent yield. All right, here's where this is okay. I can go with this. To minimize the cost of a synthesis and make the system greener, we work with as few steps as possible. One, the number of steps should be minimized. And each step in the synthesis should proceed with the highest possible percent yield. Right? That's a no-brainer. So there are two types of syntheses routes that we can do. The linear synthesis has one step. You do a series of steps to your end product. That's a linear synthesis. In this case, all you need is the percent yield for each step, and you multiply the percent yield times each one, the decimal equivalent of the percent. So the overall yield will just be the product of all those yields. So here's, let's see, I think we got a 6-step synthesis with 80%. So 80 times 80 would be 6,400. That doesn't make any sense. So it has to be 0.8 times 0.86 times. And what would that give you? Well, let's see, 51% overall.
That one says 0.26.
Oh,
For the third, it's
3 step.
The power of 3, it's 0.5.
Yeah, right. That's right.
51%, and the 6 power is 26.
There we go. Yeah. 26%. Okay, the other possibility, the fewer steps gives greater yield, that's obvious. And this chart, I mean, it's just, I think it's space filler. Number of steps and the yield per step. The thing that is unlikely to happen is that each step has the same yield. So if you have 3 steps, then you would need the yield for each one, like 50% for one, 80% for the other one, maybe 30% for this one. Then you multiply those, and that would be your overall yield. So this is simplified for equal yield for each step, which, as far as I know, never occurs. The other possibility is use a convergent synthesis. In a convergent synthesis, you have parallel syntheses, and then at some point you combine the intermediates from the parallels into a single synthesis, and then you proceed from there. So that tends to increase the overall yield as compared to a linear synthesis with the same number of steps. So here's a comparison. You have 1, 2, 3, 4, 5, 6, 7 steps. Is that right? 1, 2, 3, 6, 7.
You got 8.
8 steps. Yeah, 8 steps. Wait a minute. Well, 8, this is a precursor. This is 1 step, 2, 3, 4, 5, 6, 7 steps. Okay, so 0.8 to the 7th power would be 21%.
I'm confused because 8 and 8, 16, and that one C to the 16. So I'm a little confused.
Because, well, let's see. 0.8. If we do it to the 7th power, my calculator. Uh, 0.8 is 21%, right? So it's 7 steps in the top one, in the linear synthesis. Be 21%. In the bottom one, we have a convergent synthesis. So if all the steps are the same efficiency, then you only need to take the longest chain out of all of it. In this case, we're converging 3 steps with 3 steps into a final step. Okay, so we have 4 steps at 80%. And that's 41%. Say if you had only 3 steps in the one below, 2 steps in the one below, then we'd still take the top one because it'd be the highest number of steps.
So if you use a convergent synthesis, you get a higher yield. Is that kind of what we're getting at?
Yes.
Okay.
To end up with the same number of carbons in the process. So what we're doing is we're producing an 8-carbon precursor in the top and an 8-carbon precursor in the bottom. Bring them together to make our 16-carbon in the convergent step, and that gives us higher efficiency. Okay. Let's see. That's it for that one. All right. Chapter 21. This one shouldn't take too long because I cut out the first section altogether. The first section it was on, let's see, considerations when a synthesis calls for a new carbon-carbon bond. I figured, like I said before, I figured since there's so many bonds we've already skipped between here and 21 that adding these few is not going to help our understanding. So I just skipped to section 2. And avoiding synthetic traps. So when we, I erased it. Shoot. When we get to a situation where we have the synthetic trap reference responsible is the trap is based upon functional groups, and we want to react near one functional group or at a functional group versus another one. You have 2 possibilities to avoid this trap, and one is select your reagent correctly, and the other is to use a protecting group. Now, if you have if you're selecting a different reagent, you're selecting a reagent based upon differences in reactivity among the functional groups. So one reagent might be reactive with one of your desirable functional group and not so reactive with the other. That's one way around the problem. So here's an example. We have our tosylate is our leaving group on this compound. And if we use sodium chloride, just use the chloride ion, it will SN2 react and remove that tosylate ion. Tosylate's anion is a very good leaving group, so no problem with the chloride ion attaching to that carbon. But if we use the tertiary butoxide anion, rather than replace the tosylate group, it's going to deprotonate the carbon. And then when the tosylate leaves, it's a 2-step problem. When the tosylate leaves, it's going to form the double bond. So a selection of a reagent is selective for either, in this case, substitution or elimination reaction. So that's one way to be selective about it. And actually, This is not a case. This is regioselectivity, I think. Actually, not regioselectivity because we're attacking the same carbon. This is chemoselectivity, right? Because it's only got one functional group on it. It's got the leaving group there. That's the only thing. I mean, there's no competition. But if we use a different reagent, we get a different product. All right, so we're kind of mixing apples and oranges here, I think. Trying to illustrate the, okay. Selective reaction. Okay. We're using selective reagent to give us a selective reaction. Okay. We introduced this competition in chapter 9. Even though SN2 and E2 react tend to compete with each other, given that strong nucleophiles are often strong bases, we can choose specific reagents to selectively favor one over the other. So we want an elimination reaction. We'll choose the tertiary butoxide. And then we already talked about this one, regioselectivity, depending on the different reagents. LDA will substitute the least substituted carbon and will form the carbon bond, and the tertiary butoxide will add the methyl group at the more substituted carbon. So this is not new. How about, now we have two different functional groups here. We have an unsaturated compound with a carbonyl group on it. So we have two reaction sites. How do we select which one we want to use? Right? If we use a Grignard reagent first and followed by the ammonium chloride, then we get a methyl substitution at the carbonyl carbon, not the alpha carbon, but the carbonyl carbon. But if we use the lithium organometallic compound, we actually get substitution at the beta. So when we look at these, we have a starting compound here. And there. If we use if we use the Grignard reagent, we end up with 1, 2, 3, 4, 5, 6. Is that right? 6. Yeah. We end up with a methyl group attached here. But if we use the alpha lithium, actually copper and lithium, then we get a substitution on, well, get a substitution here. So this is the alpha and this is the beta. This would be an alpha, and this would be the beta relative to that. But this one has a pi bond involved. All right, so this is the selective reaction site for the lithium-based compound versus the Grignard. So, wish I could get that. There we go. Nucleophilic addition to an alpha beta unsaturated compound. So this is alpha beta unsaturated here. Now, this statement just makes my point, right? We skipped over chapter 18 where it would have talked about this difference, right? So you have no way of knowing. You've not been introduced to this idea before. It's just an illustration of the difference between one type of organometallic versus the other type of organometallic. And we don't have a mechanism to prove it because we never went through chapter 18. So here's a rough explanation. The weaker nucleophile with a lithium compound selectively adds to the beta carbon in a conjugate addition. So the stronger nucleophile goes for the carbonyl carbon, and the weaker nucleophile goes for the beta carbon on the unsaturated, alpha beta unsaturated. All right. Let's see. I'm not going to spend time on that. What we want, well, I will say this though. What we want out of this is to produce that end product down there in the lower right-hand corner. Well, no, they're not connected. Sorry. Now we're going to talk about protecting groups. If we change the reagents, we get a different product. If we have more than one reaction site, then we may add a protecting group. And in order to use a protecting group, we need to, it needs to be, the reaction needs to proceed on the group to be protected. The labile group needs to be protected, and it leaves the other one alone. So you form the bond, you attach the protecting group to the labile end or the labile group, and then you perform the reaction and on the remaining group, and then you deprotect it. And these are supposed to be simple, very efficient procedures. That's the whole idea behind using a protection and deprotection. So a protecting group is unreactive under one set of conditions, but removable under another set of conditions to restore the original functional group. That's the whole idea behind it. Here's an example. How would we protect this carbonyl? Well, we could just remove it and then perform the reaction and then put it back. Only that won't work, right? You can't deprotect a fully saturated carbon, right? So that would be a poor choice as a protecting group. However, if some way we could form an acetal from a ketone or an aldehyde, either one, then that could be readily reconstituted as a carbonyl group. So we perform the reaction. That site is protected. We perform the reaction, change A to B in this case. And then all we need is water in acidic conditions, and we can reconstitute B. So that would be a good choice for protecting a carbonyl group. Aldehyde, acetal. Actually, it looks like it's got two ether groups. That's an acetal. Let's see. This would be an acetal. And this would be, in case you ever run into it, this would be a hemiacetal. You see those a lot in biochemistry. So when you get to the carbohydrate discussion of carbohydrates, you'll see hemiacetals all over the place. So they're resistant to strong bases and strong nucleophiles. That's good. They resist oxidizing, reducing agents. And we do it by using alcohol acidic conditions. We can recover the carbonyl simply by hydrolyzing the acetals. Here's another possibility. We can form a 1,2-diol, a cyclic diol, actually. No, with the diol as the reactant, excuse me. The diol is the reactant, and it forms a 5-membered ring around that carbon. It's also an acetal, but it's a cyclic acetal. And then all you have to do is hit it with acid and water, and it reconstitutes. Ethylene glycol. You know ethylene glycol?
Isn't it like kind of thick?
Yeah.
It's like, I've seen the name before and I know it's thicker, but I don't really know what it's for.
You put it in your radiator.
Okay.
Yeah. Antifreeze. Yeah.
Okay, yeah.
50% ethylene glycol is usually the standard for antifreeze in your radiator.
Mm-hmm. Yeah.
Tastes sweet. That's why I keep it away from your dogs.
Yeah. I remember that now.
Because they'll drink the bowl and it'll shut their kidneys down.
But it doesn't taste sweet to us, does it?
Slightly, yeah.
Slightly.
Mm-hmm. It's probably because of those alcohols. Because sugar has lots of hydroxyls on it. Yeah, a friend of mine had his dog killed by someone who left some ethylene glycol inside the fence.
Yeah. That really sucks.
I don't know. Couldn't find out who did it though. Okay, I'm going to go on. All right. So this product has the product we want has two. Let's see. Well, actually, if we're starting, that's only one functional group on that. But at some point, I think we're probably going to end up with a situation where we have more than one functional group in order to get to where we want to go. I think we're going to skip that. Yeah. This would simply protect the Grignard reagent so that you get reaction. Okay, I see what's going on here. We want the Grignard to react only from the carbon side of the Grignard, for the magnesium side of the Grignard. All right, so we protect the carbonyl group on the other side of the Grignard. Yeah, protect the Grignard on that other side. We protect the carbonyl on the other side until we get finished with the Grignard, and then we reconstitute the carbonyl. Okay. All right. These are protecting groups for alcohols. All right, so it doesn't have to be the methoxymethyl ether. Ethers are very resistant under strong nucleophile and strong base conditions. All right, so they're good protecting groups. Looks like a lot of them are ethers. What's this TBDMS? Tertiary butyl dimethyl silyl chloride. My goodness, that's a monster. We can protect diols by forming a cyclic compound. Right, that's acetone right there. On top of that arrow. And then reconstitute it with water. That seems to be a trend. If you can reconstitute simply by adding water and acid conditions, that's pretty simple.
And greener bread.
Oh yeah, exactly right. All right. I'm not going to spend time on that. So basically, what we get out of that is two ways to avoid the traps. Right. Change your reagents or use a protecting group for 21.